Okay, in this problem I'm going to be doing something in my dynamics class. Um, this is a problem that you would usually see in physics. It says an elevator descends. Okay, so we have an elevator and it's descending from rest with an acceleration of 5 feet per second squared until it achieves a velocity of 15 feet per second. And they want us to determine the time required and the distance traveled, okay? So they want us to find this time required and this distance traveled. And like, look, we can just draw a little picture of this. We got a little elevator. It's traveling that way. And it's descending from rest. And what that means is that the velocity initial is 0 feet per second. And it travels with a constant acceleration of 5 feet per second squared. That's what I have right here. So I already, wrote down what everything is. I just wanted to put the picture on there to make it more clear what we're dealing with. We're dealing with this elevator right here. So anyways, knowing this information right here, this given information, this problem is relatively simple to solve. Now, anytime you're dealing with constant acceleration, you can use these formulas right here. You can say the final velocity equals the initial velocity plus the acceleration multiplied by the time. We can also say, we can also use this formula right here. Velocity final squared equals velocity initial squared plus 2 times acceleration times the change in distance. And we can also use this formula right here. Change in distance equals velocity initial multiplied by time plus 1/2 multiplied by the acceleration multiplied by the time and the time squared. Now these three can only be used when acceleration is constant, okay? Also, formulas that could be used would be velocity equals the change in x divided by the change in time. Acceleration equals the change in velocity divided by the change in time. And you can also, one that comes up quite often is v dv equals a dx. Okay. And on this one right here, it usually ends up going like this. You would say v dv equals a dx. So you would do x1 like x2 and like v1 to v2, stuff like that. So anyways, on this problem, what do we have? We have the velocity initial. So we have this right there. Let's see, I'll change colors to like red. We have that. We have the acceleration, and we have that. Now they want us to find the time, so look, we could find that time right there with this equation right here. With this equation right there. They also want to know the distance. Well, if we found that time right here, well, since we know the velocity initial, we want to know the change in x, so that's what we want to solve for right there, right here. Well, if we found the time earlier, then we would know that, and we know the acceleration. So then you could use this equation right there to solve for the distance traveled. So that's what we're going to do. I'm going to go ahead and solve this. I'm going to go ahead and just copy what my notes say. And we're going to end up using, let's see, whenever I was doing this, I did velocity final equals velocity initial plus acceleration multiplied by time. And then you manipulate this equation and you can say time equals velocity final minus velocity initial divided by the acceleration. And that's going to be 15 minus 0 divided by 5. And that's going to give us 3 seconds. Now I didn't put the units in there, but you can if you want to. But all the units will cancel out. and you'll be left with 3 seconds for the time. So now that we know that the time is 3 seconds, we then use this formula right here. Change in x equals velocity initial multiplied by time plus 1/2 multiplied by acceleration multiplied by time to the power of 2. And then we just plug and chug. We're going to say the change in x, and since the velocity initial was 0, you're going to have 0, and the time was 3 seconds. I'm going to put the units in this time. Plus 1/2 multiplied by the acceleration of 5 feet per second, and then multiplied by the time for 3 seconds, and that's squared. So then that would be 0 right there, so I'm just going to scratch that out. And the 3 to the power of 2 would give us 9, and then when we multiply that by 5, it would give us 45, and then when we divide it by 2, we get 22.5. So the change in x equals 22.5 feet, okay? And if you want to look at the units, well, this would be, let's see, I'll just say just forget about the units. So you're going to have 22.5 feet. The reason why I was saying forget about the units, well, I just know that it ends up working. And let's see, we have feet per second, and then this second's going to be squared, so you're going to have seconds squared. So then you're going to end up with, oh, whoops, my bad. This is why I was confused there for a second. This should be squared right there. So these squareds cancel, and you're just left with feet. So there's your solution for your change in distance. That's how you solve this problem right there. This is a good refresher for these. Basically, this is a refresher on this formula, this formula, this formula, this, and this formula. And you need to know that these can only be used when acceleration is constant. The rest of it was just, just plugging and chugging and stuff, but these formulas right here are what's necessary. That's something that you need to know whenever you're dealing with rectilinear motion. And that's one thing that you need to realize was this problem was rectilinear kinematics, and that's basically the study of the motion of an object that's going in a straight line. I do believe that's correct. I'm going to check my book real fast to verify that. Rectilinear kinematics is the kinematics of a particle is characterized by specifying at any given instance the particle's position, velocity, and acceleration. So rectilinear kinematics is solving for a particle's position, velocity, and acceleration, okay? So a rectilinear means a straight line or path. And you should remember that a particle has a mass, but negligible size and shape. Therefore, we must limit the application to those objects that have dimensions that are of no consequence to the analysis of the motion. In most problems, we will be interested in bodies of finite size, such as a rocket, projectile, or vehicle. Each of these objects can be considered as a particle as long as the motion is characterized by the motion of its mass center and any rotation of the body is neglected. So whenever you're dealing with a particle, when you're doing rectilinear kinematics, you have to neglect the object rotating and it just travels in a straight line. But anything can be a particle, like a Boeing 747 or something like that, or a car. It can all be considered a particle. A particle isn't necessarily something that's really tiny. It's just we neglect the object rotating, and it has to travel in a straight line in this case. Anyways, that's the end of this, and if you want to read more on this, Jonathan, you need to check page 5 in your dynamics book. under rectilinear kinematics, continuous motion.